זה בהרבה מקומות שם, נכון, יש כאן איזה הבדלי תרבות.
אז זה גם כמו הרצאות, זה מחולקים לשעות?
כן. כן, וגם מדעי הרוח יש עניין של לקרוא מהכתוב, לא תמיד, זה יותר אולד סקול. היית בזה?
הייתי...
כן.
יש סיפור של...
כן.
שגריר, שפעם ראשונה שנתן פה הרצאה,
כן? מי היה?
רון שגריר.
אוקיי, כן, כן.
נכון, זה רון שגריר סיפר על הפעם ששפיגה ב-ELSC?
יכול להיות, אני שמעתי את רון מפרי הרצאה מהדף, גם מי שעשה את זה אצלנו. איך קוראים לו? מי שהיה שר בממשלה, פילוסוף.
יובל שטייניץ.
יובל שטייניץ שמענו פעם מקרי.
כן.
אפשר להקליט היום אפילו זה אייג'נט.
כן,
נכון.
נכון.
זה נכון,
היה להם הרבה זמן בעיה עם הפרוזודיה, אבל אני חושב שזה גם מאוד משתפר. נכון? כאילו יש...
זה נשמע, כאילו שזה נשמע...
כאילו, אתה יודע, כאילו האינטונציה, והפיץ' קונטור,
אז לא יודעת, אני ממנו רואים,
כן, נכון. זהו, כבר לא שומעים. זה הרבה פחות מתכתי. הבנתי שהמתכתיות זה טוב מאוד. כן, זה כל העניין של האמפליטודה הנמוכה, נכון? כל התדרים כאילו, כל האפקטים יותר עדינים. נכון. כן. מה?
חוץ מה...
כן, כן, זה בסדר. באמת? מי? התלמידים?
מי שירת אפליקציה הוא לא לשם הכבוד.
לאיסוף דעת?
אמרתי, מי שיש לי תואר שלישי מאוד, זה סודם לא לשם הכבוד.
כן.
אנשים לא מכובדים. אנחנו נציע כמה רעיונות סופי, למשל, אנשים יצביעו אחד הרעיון שלהם לתרגום מה אתה בפייתון,
כן.
אסטרקטור, מה אתה בפייתון, שאנחנו מתקנים את זה כל הזמן. Okay, thank you everyone for coming. So today we have abend from the computer science and from the cognitive science department. He works in computational linguistics and natural language processing with a long-standing interest in how to represent meaning and structure in language and how it can be computed. He's well known, among other things, for his work on UCCA, which is a semantic framework for language representation. Today we will discuss computational approach to fair play and narrative, which is using detective fiction as a case study to formalize the trade-off between coherence and surprise. And I think this is a topic that would be relevant to many of us here, not only for people working on language, because it has the idea of expectation, inference, and surprise, things that we kind of tackle onto them in neuroscience all the time. Thank you. So we have an hour, and then we talk.
Thanks. Okay, thanks for the intro. Right, so this is joint work with Eitan Wagner, a PhD student who's jointly advised with Rana Heida, another co-author of mine, and really the person to thank for working on narrative, because as Jonathan mentioned, this is not the topic that I was traditionally focused on, but as I'll try to argue here, there are many interesting computational questions. What did I do? Many interesting computational questions around it. Okay, so first of all, why stories? So stories are, of course, a cornerstone of many types of scholarly investigations, right? They've been studied extensively by anthropologists, psychologists, education, scholars of education, and so on and so forth. But even more specifically within the field of AI and specifically NLP, story generation has been a field of investigation for decades now, both because it represents an interesting test case for language or for text that has a particular relatively rigid in a sense, as we will see, structure. And also an interesting test bed for looking at things such as informative reporting, persuading, and it is also, as I will explain towards the end of the talk, is also related to fundamental AI topics that go beyond the text and the NLP, and specifically theory of mind. Okay, so within the field of computational narrative analysis, I would like to focus on a subtopic called generic conventions. Okay, so the idea behind generic conventions is that when you as a reader read a story, or when someone as a writer writes a story, there is a certain implicit understanding, right, between the two parties as to how the story will be constructed, what's considered conventional, a typical story. And of course, usually good stories are not just some implementation of strict guidelines that would be somewhat boring, but rather they have a certain dialectic relationship with conventions, right? So this is a nice quote. The reader demands compliance with the established generic conventions so that he can integrate the new text, but at the same time, he expects the writer to manipulate these established conventions so that the new text is more than a tedious repetition of the generic tradition. Okay, so that's interesting for computer scientists, certainly, right? Because we're talking about structure here, right? We're talking about structure, and we're talking about an interesting relationship with this structure, probably a much more nuanced one than, for instance, if we look at grammatical rules, which tend to be far more rigid than these generic conventions. Okay, so what do I mean specifically when I say generic conventions? People use this term for many types of schema, right? Many types of schema. One typical one is the event-based approach, basically representing a story as the progression of event types. So perhaps you could guess what type of story, right? What type of narrative looks like as follows: meet cute, conflict, big gesture, and then happy ending. Romantic comedy, right? That's very typical. That's one that's more, I guess, more of a movie genre, but never mind. This also has a fairly rigid structure, right? Sometimes there's some manipulation over it, but yeah, character-based approach. Many types of characters that we are used to re-encounter, right? With many different types of stories, many different types of movies. For instance, The Old Wise Mentor, right? So here are a few nice examples from recent movies, or some of them not so recent ones. But I will focus here on another type, which also has a fairly long history in literary scholarship, another type of schema, which is progression along some semantic dimension. Okay, so this is a diagram taken from a talk given by Kurt Vonnegut. And he basically proposed in this talk, you can also find it on YouTube actually, very funny talk, but basically what he was arguing is that you can distinguish between genres by the way that the protagonist gains fortune or loses fortune, right? So here we have the y-axis is the good or ill fortune of the protagonist, and we have the narrative timeline, that's the x-axis. And then you have, boy meets girl, maybe right some improvement, then big dip, and going towards infinity as the story progresses. And you have men in whole, and so on and so forth. Now, this is of course still not a complete formal presentation, but Wilmot and Keller, and this was, I guess, the main initial inspiration for our investigation, in 2020 showed that you can model suspense, right? The suspense that the readers at least report when reading. In this case, I think it was scripts of also some crime drama. But basically, what they showed there is that you can use uncertainty reduction, right? The statistic of uncertainty reduction, and computed using language model probabilities, right? So probabilities induced by a language model as a strong predictor of suspense. And that's interesting, right? Because suspense is, well, you would expect perhaps that suspense would be a kind of a multi-dimensional, very subjective issue, very difficult to model, but here they pretty much showed that their language model, built in a certain way, but never mind that, is a strong predictor of success. And there's, of suspense, sorry. And this, in a sense, is related to, I think, a now fairly established line of work in psycholinguistics, the ties between probabilities, often also produced by language models, with the notion of surprisal, right? And that is related, has been shown to be related with reading times, event-related potentials. So this whole general topic, and of course there are many niceties here, but this whole general topic of the extent to which the reader is surprised, or the extent to which the reader, experiences suspense, and so on. These are things that there's already quite a bit of literature about how to tie LM probabilities with them. Okay, the case that we were interested in was detective stories. And detective stories were interesting for us for a couple of reasons. First of all, they also have this element of surprise, right, in them. A good detective story, and I'll be talking about the whodunit detective story, okay? So there are other subgenres, but one, right, in which we'll see it, but the culprit is unknown and should be revealed. So it has this quality that the reader should be somewhat surprised by the resolution of the story. But on the other hand, the reader should also experience somewhat sometimes called coherence, right? Essentially, the experience should be that the resolution is surprising, but then again, when thinking about it, it also makes sense, right? I should have known that the butler did it, right? Had I only connected the dots correctly, okay? Now, never mind if this is indeed the case. This is what we often expect from a detective story, to achieve this balance between having the surprising resolution and a coherent one that makes sense. Okay, and taking this idea of progression along a semantic dimension, we thought it was natural to look at tracking the identity of the culprit, or the perceived identity of the culprit, or the distribution over possible culprits along the story. Okay, so that would be the dimension that we will try to characterize story along. Yeah, maybe that was grammatically informed, but anyway. Okay, so we want to define a measure which tries to capture the story's ability to maintain the surprise coherence balance. And this is diverges, or to some extent extends, previous work that looked at a single dimension such as suspense, surprise, or related issues. What we will try to do is try to distinguish, using this measure, between good stories, right, or stories that are able to maintain this balance, and ones that do not. Why would we want to do that? Well, I tried actually at one time, I think it was a year ago, to give a talk where I said, well, this is a very important thing to do because then language models will be able to write better stories. Now, maybe this is the case. I should say that it's a bit dishonest of me to argue that this is the main motivation here, because it certainly wasn't my motivation, right? I was just interested in whether you can cast this elusive notion of, the surprise coherence balance in computational, in this crude computational language model-based terms. But maybe that is possible. And towards the end, I will show some connection perhaps with theory of mind, or argue that there might be a connection. But mostly my motivation was just to understand stories in computational terms. Okay, so what is the structure of whodunit stories? How do they usually look like? And I'm sure that this will not be very new, but just to put things on the table. So the structure of whodunit stories usually consists of 3 steps. In the first, you have an introduction or an exposition. Some crime is committed, say a murder or some theft, right? The characters are introduced. It's usually, at least in the classic whodunit stories, it's usually a closed set of potential culprits, right? There is some manor house away in the countryside, or a boat, or a train, or whatever, right? You know who the possible culprits might be, and some crime is committed. Then there is an investigation. Often there is, or usually the case will be that there will be a brilliant detective, such as, say, Hercule Poirot, right, perhaps one of the most famous examples, and they start to conduct an investigation, gather clues. Sometimes there's also a sidekick, right, considerably less competent detective who also has an interesting, important role in the story. We'll see that in a moment. Some stories do not have such sidekicks, and then in the end you have the revelation or the resolution. The culprit is revealed by the detective. The clues are resolved. Okay, and what we want, the quality that we want to achieve, is sometimes called fair play. Okay, so fair play basically means that there is a mystery to solve, okay? That it should be surprising, okay? It shouldn't be just obvious who the culprit is. But then the reader, or some have, cast this notion of coherence as saying the reader can solve the mystery if smart enough, okay? So that's one common notion of coherence. And then you might say, okay, if you managed to write such a story, then you achieved fair play. But you can also write fairly easily. You can also write detective stories who are surprising, but unsatisfying, right? In the sense that the reader could not have solved them. And this is, for instance, a part of the story by the up-and-coming author Lama 3.170b Instruct. So in this case, there is a story, and there's a set of potential culprits, and so on and so forth. And at some point, after trying to piece together the different clues, this is what you get. So just as Jameson was about to press Olivia further, his phone buzzed with an incoming call from the police station. Ta-ta-ta-ta-ta, and get this, we found the security camera that caught her entering the Langley estate around 10 p.m. just before the murder. Essentially what happens in this story is that you try really hard to figure out who the culprit is, but then at the end of the day, there's just footage of the person who did it, right? It's simply completely unrelated to anything that came before, and that's it. The story is resolved. Certainly a surprising outcome, but not a very satisfying. Okay, so this is sometimes called Deus ex machina, right? God from the machine. Okay, so what's the modeling approach here? How do we think about it? Okay, so the main notion that the framework is built on are the reader models. Okay, so essentially we envision different types of readers who might read the story and track the probabilities, the distribution of the culprit as they, as they continue reading the story. So along the narrative timeline. Okay, so on the left-hand side, we have the brilliant detective reader. Okay, the brilliant detective reader, we think about it as it's an idealized reader, right? Who simulates, say, Poirot, right, or Sherlock Holmes. He makes the best possible use of the clues, right? So that the brilliant detective makes optimal use of the information given to them. Okay, so that's one end. On the other end, you have the gullible reader, okay, who's sometimes depicted in the story itself, right, like Hastings, say, or Watson, or whatever, or the clueless police investigator, depends on the type of story. But that person is exposed roughly to the same information, that reader is exposed roughly to the same information, but makes poor use of this information available to them. Now, of course, these readers, we call them internal readers because we think of these readers as readers that try to simulate a character within the story, right? But when we read a story, we actually get more we get more information than what is available to the characters. For instance, we know the order in which the characters are presented, okay? Right, we know they're presented in some order in the exposition. Usually this order is not some chronological order or anything, it's just the way that the story is. But perhaps some writer, okay, this will be important in a minute, perhaps I, as an author, always present the culprit as the third character. Okay, the third character that I write about is always invariably the culprit. Okay, this information is not disclosed, cannot be available to the internal readers, so that's why we have a know-it-all reader who's even better, in a sense, than the brilliant reader because they have more information and they also make optimal use of this information to resolve the crime. And hopefully, presumably the actual reader, any reader is usually somewhere here, right? They are reading the text. They're not inside the story, so they are external in this sense, but perhaps they're not as good as the optimum, and perhaps can say a few words about that later. Okay, so that's these are the different detectives, and here's the way, and then perhaps if we have ability to compute these predictions of the different readers, then we could define fair play as, or a story that has the fair play quality as one where a brilliant reader, right, as one where when the brilliant detective receives the information given in the story along the narrative timeline, their graph, right, their probability, say, of the true culprit, or their whatever relative entropy relative to the to the identity of the true culprit or whatever, looks like this. Okay, so it rises fairly moderately, but then the gullible reader, right? So a different type of reader who is exposed to these clues would pretty much not know anything. Perhaps somewhere in the middle would even be distracted by the distractors, right? The culprit who the author now planted inside, so that the gullible readers would be led astray. And then in the end, of course, there's resolution, and then everyone knows who the true detective. So they, right? So they're both equal one or whatever maximal success. And then we might say, okay, well, a good story is one where there is a gap between them. A bad story, such as the one given here, would, if this works correctly, will have the blue and the orange lines roughly coincide, okay? Because there's really nothing to be gained from tracking the clues, right? You really have nothing to do with them. So gullibility is as good as brilliance in these stories. Okay, but of course, this is an idealized picture. So how do we actually do that, right? I mean, how do we know what is the optimal distribution, right? The best way to use the information given in the story, as opposed to a rather gullible way to read the same story. So that's the yeah.
Is there any memory limitation? Do you assume that at any point the reader had all the he has forgotten things?
So you mean for the gullible one?
For anyone, because there's two things. One is to remember everything, and the other one is which is finite number of information, and the other one is exponentially large, which are all
Yeah.
the options that you can combine them together to get something.
So that's a good question, and we tried to think, we at some point tried to model, I'll now show you a way, a specific implementation or bounds on, these curves. So one of the directions we try to pursue for the orange one is one who has limits, so only looks at, the immediate the immediate clues, right? So at some point of the story, you just ignore whatever was. But that didn't really, that didn't really look the way that we expected it to look, so we simulated it in a different way. But perhaps I'll show you how we did that, and then you
Markovian
can...
reader and a non-Markovian reader.
Sorry?
A Markovian reader and a non-Markovian.
Well, no, much more, I guess, common NLP perspective. But I'll talk about that in a second. First, let me start with the know-it-all reader. Okay, so the know-it-all reader, that's a big issue, right? Because the know-it-all reader, we say we want it to be an optimal detective. Okay, why do we even want the know-it-all reader? Because the know-it-all reader bounds the brilliant detective reader. And not only does it bound it, in a good story, they should roughly be similar. So let's think about it for a moment. What would be a story in which the know-it-all reader, okay, the one reading the text, okay, and making optimal use of what's given in the text, is much better than one who's just exposed to everything described in the text. So that would be, for instance, the author where always the third person mentioned is the culprit, or it's always the butler who did it, or it's, I don't know, all sorts of things we usually don't want. We want the clues inside the story to be sufficient. So at least in a good story, we would expect this not to be too big a gap. So perhaps we can try to model this using this. Okay, and why do we want why do we want to bound them? Because for the know-it-all reader, we actually have a way, at least in theory, to compute their probabilities. How do you do that? So yes.
Can you define it? I mean, you gave an example.
Yeah. Now
we'll define the difference between the brilliant and the no.
Yes. Though I'll define the know-it-all, and the brilliant I'll only be able to define it softly. But in the end of the day, the only thing that would matter is that the know-it-all is an upper bound over it. But perhaps I'll explain, and then maybe you can ask me again if it's not clear.
What kind of information the know-it-all has?
So the know-it-all has all the information. Now, what does that mean? Okay. So what does that mean? So here's the way we chose to model it. Okay. What we're saying is, well, in order to understand what the know-it-all reader would guess, you need to assume that you're not looking at one particular story, but you're looking at a population of stories. Okay, so you're looking at the probability measure over stories, and if this is the case, if you're looking at probability over the stories, if this is the case, you can say, okay, say I have read the story up to the middle. Okay, so here's now I have the prefix, the first half of the story. Okay, in theory, what I could have done, right, is say that I have a fixed length. Okay, we looked at short stories. Beyond that, things tend to be, the technology is not there yet. But we have short stories, 25 paragraphs. Okay, so we know the length. What we could do if we have only the first 12 paragraphs is, at least in theory, we could look at all the different ways to generate the next 13 paragraphs, right? Each of them would end in a leaf. Of course, you'd have gazillion leaves, okay? But in theory, you'd have a gazillion leaves of all possible stories, each of them with their probability, okay? Again, if you have this now, in each of them, there is one culprit, right? One culprit exactly. It's a one-point mess, because we assume that there is a resolution in the end, so it's a one-point mess. Now what you could do is just marginalize over the culprits, okay? And this is, and this means, and if you know this, so if I as a reader know the distribution, know the generating probabilities, then I really know everything. I mean, if you assume that, right, if under these assumptions, then I really know everything, okay? There is really nothing more to know. Now you might ask, and this is a very natural question to ask, well, but people don't really write stories this way. I mean, they don't write, I mean, maybe language models do, certain language models certainly do, but why, you're talking about stories, right, in general, why would you think that this strange notion of a population of stories that has a probability measure over them, why do you think this has any relevance to, to literary scholarship? Well, it turns out that there is a parallel notion in literary scholarship. That was someone who listened to an early version of this talk actually gave us this connection. So it turns out that Charles Dickens died while he was writing his last book. Okay, he finished roughly half of it. It was a mystery. It's called The Mystery of Edwin Drood. Okay, so he finished half of it, but the identity of the culprit was not disclosed in these 12 chapters. Not only that, also no one was able to find a notebook or notes or any external indication as to who the intended culprit was. Okay, and now came the literary scholars, right? And what did they do? Well, they tried to figure out not who the most likely culprit is under the world, painted by Dickens. No. What they would try to say is, let's think what the, whatever, 80-year-old or whatever Dickens writing this story, what is the most likely culprit, had we been this person, what is the most likely culprit for, what would that person be for us, for him, right, for Dickens? And of course, there were many discussions. People were not able to agree on anything, but at least the theoretical construct does exist, right? So there's no need to imagine that there is necessarily a generative stochastic process that, that generates the story. That could be the case. Certainly, if this is the case, that would be nice for us, because then we have access to this measure. But also, if you're just and imagined Dickens in his late days, right? There are all the different stories that person could write, and at least in theory, you could think that there is some distribution over them and try to marginalize over it.
And by contrast, the brilliant, what does the brilliant reader lacks?
So the brilliant reader lacks is that for instance, he does not know that he is now or she is now in a story written by Dickens in his late days. Perhaps that person, like Truman in the Truman Show, right? They think that they don't know that now this commodity used by their wife is actually part of a commercial, right? It's just what happens to them. But the thing that would matter for me is okay. Two things would matter for us. First of all, that the know-it-all reader is an upper bound on the success. In fact, this was not difficult to do, right? Because we simply defined the quality or the success of a reader as the relative entropy relative to the know-it-all reader, right? And then, if you buy this definition, then clearly the know-it-all reader is the best, is the best you can do. Its only failures is due to the very entropy of the distribution. So that would be one thing that's important for me. And another thing that would be important for me is that the gap between them is not too big. And for this, you can try the way that we try. If you have other ideas, I'd be glad to hear. But the way that we try to, at least to estimate whether this is in fact a confound in our experiments was by training a reader who's, we called it the experienced reader. So essentially, say you have a generative process, like a language model. That's much easier than human authors, right? So you have a language model. Then what you could do is produce many stories from this model with the same prompt, and now let a reader train on these stories. So now, if for instance, so that doesn't completely prove it mathematically, but for instance, if you would see that the experienced reader still so that the experienced reader, basically what you would want from them is not to close the gap with the know-it-all reader entirely, I think, right? Because that would mean that the additional information that you get by just looking at a few samples from the same distribution, if you close the gap entirely, that means that you really have a lot of information that's outside the story, perhaps, that's at least one interpretation, that's outside the story. So maybe I'll frame it, I'll say it differently. If I'm a writer, okay, and for instance, let's look at this. If I'm a writer and there is something in the words that I use, in the order that I present, some superficial pattern that in the text that I write that allows you to figure out who the culprit is, for you as a reader. It's some regular expression, whatever. Then if I train a model to predict who the culprit is on the n+1 story based on the first n ones, probably if my neural net works right, then I'll be able to solve it, right? That's it. Even without looking at a new story, in a sense, or just by looking perhaps at a fairly impoverished representation of the next story. Yeah, but certainly that is, so for us what would be important here is that it's an upper bound, mostly. Okay. Okay, good. Now, so we defined it. I'll put a link at the end if you're interested. But basically, the way that we defined all these, given formal information theoretic definitions, right? The success of a reader is the extent to which this reader is similar to the know-it-all reader. And you can actually prove formally under these definitions, it's not very difficult, that there is indeed a trade-off between being, for a particular reader, okay, for a single reader, there is a trade-off between the extent to which that reader is surprised and the distance of this reader from the optimal reader. Okay, so let's call the distance from the optimal reader the intelligence of the reader, okay, so the ability to make similar predictions to the best possible predictions that one could make. So if I'm intelligent enough, then basically I cannot be surprised, okay? I cannot be substantially less accurate than random. Well, of course, unless my clues are completely ineffective, okay? So I need to also assume that, because otherwise, if I have clues that really have nothing to do with anything, then of course I could be surprised, but that's an unwanted outcome. Okay, so we defined this framework. We're pretty happy with the formal, framework and being able to prove something about it formally. But of course, what we want is to have, at the end of the day, to have some statistic we can compute based on LM probabilities. So for that, we looked both at generated stories and real stories, where of course the difficulty here is that on the one hand, you really want real stories to look at, because while LLMs get better at writing stories, certainly short stories, these stories are, I don't know if, does any of you read LLM generated stories occasionally? No, it's not very popular. Some people do. Actually, I have a friend who reads their bedtime stories for their kids are LLM generated. Sorry?
There's a whole genre of Reddit stories of like, am I the asshole, or like some story about, like they're totally generated by AI.
Okay. And some people like them because they can control them, right? They say, now I want a story about children's story about the duck and the turtle. So, oops, you have a story about the duck and the turtle. Okay, maybe it's not a very good one, but sometimes you don't care.
It's also like stories about like just stories about like, it's also very like, I guess what will happen in, I don't know, it's still talks of, but it will be very like, there will be like the story settings that will be similar, like those Reddit stories, like people did me something wrong, I took revenge, and I'm better than them, I'm better off without my ex, he cheated, and insane, like the butler did it, the maid did it, I would assume.
Mm-hmm. So you're saying that they're too...
It's very formulaic.
Yeah, that they tend to be too formulaic. Yeah. Right, so obviously it's not ideal, but on the other hand, there we do have the generating distribution, so that's nice. With real stories, we don't really, so we looked at Hercule Poirot and Sherlock Holmes. Now, of course, for these, we had no way to actually interview Agatha Christie or Arthur Conan Doyle, but what we could do is try to simulate them, so we still need to sample from the different continuations, right? We don't really want to marginalize because it's intractable, but we can use Monte Carlo, which is also very costly, actually. So the cost here is an issue. But at least, after some relaxations, it was manageable for not a very big set of continuations, but we could do Monte Carlo, and that's what we did. Okay, so that's for the generated and the real stories. We also wanted to, in some sense, compare them with manual annotation. So we gave annotators almost the exact same task as we gave the language models. The language models, we gave them a task to output a distribution over potential culprits. And, at least in the theoretical framework, we looked at the cross entropy of that distribution from, the true distribution. Now, for people to ask them to give a distribution over culprits with probabilities, we decided against that. Instead, we asked them what is the mode of this distribution in their mind. Okay, so what do they think the most likely culprit is? And then we also took the reader models and had them output only the mode, so it would be comparable. Yes, so we looked at 54 generated stories, 11 real ones. Each story was annotated by about 5 annotators. For surprise, what we did was, so here we built on, so I think it relates to your question, Jonathan, we built on previous work who showed that, some notion of surprise can be captured with language models. But the problem is that it turns out that recent advances in language modeling have made them worse predictors of surprise, as defined, say, by reading times or ERPs, because they're too good, in a sense. So we asked them to be gullible. Okay, we simply asked them. As I mentioned, we try to ask them, to just give them a more limited context, right? But the difficulty is that some clues are very prominent. So you really expect any reader to remember at least some prominent parts of, of what came perhaps at the beginning or considerably before.
So why not give it chapter by chapter, ask it to summarize, and for the next conversation start with a summary.
So some kind of bottleneck, you're saying.
The idea is to remember. The question is, does it remember what it needs to be remembered? Because that's when you have capacity, not.
So you have to decide now what to remember for later. Okay, that's a cool idea. We'll try that. But what we did was just ask it to be gullible. And of course for coherence, as I said, use Monte Carlo. So then we can define a human coherence, right, or the counterpart of coherence, as the area under the average. We took the average reader, right, of the annotators, of the 5 annotators, and you can also compute fair play with still using the same surprise. So really, fair play human is coherence human and the same simulated surprise as we had for the automatic readers. And this is basically what we found. So we took different types of LLMs. I don't know how, Llama 3 is an open weights model by Meta. We took various sizes and variants. Some of them not particularly good, right? Considered somewhat outdated by now. Some of them are okay. Gemini, right? Some of them the more recent ones, the less recent ones, the Flash versions. the pro versions who think more, and GPT as well. So what we found was, first of all, weak LLMs. So some of these LLMs, I'm talking all about modern ones, right? Like billions of parameters, or at least 1 billion, usually 7 billion and above. But the weaker ones do not even meet the admissibility criteria, right? So they don't necessarily even, although they are instructed to output one culprit, at least one distractor, and so on, they don't necessarily do that. So that is, these ones are, of course, rejected. Larger, newer models basically follow the guidelines, right? So comparing GPT, X versus GPT X plus 1 or whatever does give you more admissible stories according to these admissibility criteria. But nevertheless, surprise does not turn out to be correlated with coherence. So I'm now talking about the automated versions, right? The Monte Carlo and the simulated gullible detective. They're about zero correlation, roughly. So in this sense, it was, I think, a good outcome for us, in the sense that bigger models are able to follow the instructions better in terms of constructing the story in the right way and having one culprit and another distractor and so on. But they were not better at simultaneously, maintaining surprise and coherence because they go against one another, right? They pull you in different directions. Another validation that we looked at was to look at the coherence versus the human coherence, which perhaps I should say it's not exactly coherence, but the average human performance, right? That's coherence. So what we would expect is that if you have, so remember the LLM coherence, at least if we manage to compute it correctly, right, that's an upper bound, right? That's the know-it-all reader. That's an estimate for the know-it-all reader. So that means that that you should not expect a high human coherence with low LLM coherence, right? The other direction is perhaps more plausible because it's an upper bound. But if your estimation is okay, you should not expect anything in this area, right? High human coherence and low LLM coherence, and this was another indication of that. So that was also, so these are all validations, of course. All our experimental setup was mostly to validate the framework. The Poirot versus Holmes stories. So the intuition, well documented in the literary studies and also very intuitive, is that the Holmes stories are not classic whodunit stories in the sense that you usually have a pretty good sense in most Holmes stories, not all of them, about who the culprit is. But the thing, and Holmes figures out how to actually prove that, right? Or how did that person do that? But often with Conan Doyle, you have this sinister looking, character showing up at some point, and that person turns out to, in fact, be the culprit. So the mystery lies someplace else. And indeed, we see that also for the gullible reader, the Poirot ones are, again, these are all averages, but the Poirot ones are pretty surprising, right? The true culprit doesn't gain considerable probability before rather late, and so that's the surprise alternative, that's the gullible reader for the Poirot, and for Sherlock it does, despite its gullibility. Right, for the actual readers, it's less pronounced, but basically we also see that the human readers agree with this idea that, or this intuition that the Poirot story really, gain near one probability later than the Sherlock ones. And we also looked at self-reported judgments, right, so not ideal, but try to get another validation. So simply asking the readers, the annotators, whether they found the story surprising, coherent, fair. Now, surprising is pretty much intuitive. People understand what a surprising story is. What a coherent story or a fair story, perhaps this is, much more dubious. But we try to compare them with, with our notions of surprise as computed by these graphs, and fair play. We try to compare with coherence, and so on. So there are natural counterparts. We found positive correlations throughout, but they're not particularly big in terms of their, the correlation themselves. Were not particularly big in terms of their absolute value, which I guess indicates what we should probably have known, that there are many other indications that go into these self-reported notions other than this fair play quality that we looked at. Okay, so I see I only have 10 more minutes, so let's skip these examples and conclude. So detective stories should be both surprising and coherent. These notions are in tension with one another. A good story should maintain a balance between them. We use the probabilistic modeling approach to capture this balance as a trade-off between the two perspectives, the naive or the gullible and the informed or the brilliant one. We propose a way to compute these metrics, or at least proxies to them, and show some empirical validation. My concluding note was about future work that we hope to do, hopefully soon, is trying to relate this discussion to a very popular discussion now in the literature about, do LLMs have a theory of mind, right? I don't know if you've been following this. There's an abundance of papers and ways that try to actually evaluate to what extent an LLM has an ability to have a theory of mind. Most of at least the initial work along these lines looked at Sally-N tests, which I guess I'm sure some of you know, some of you do not, or maybe all of you know about Sally-N tests. Okay, so Sally-N test, the idea is simple. You basically have say that we are. So how do I do that? Let me just read. James and Abby are in the bedroom. Abby put the pen in the desk drawer. Abby leaves the bedroom. James moves the pen into the bag. Okay, so now you're asked, where does James think Abby will look for the pen? And the thing is that despite the fact that right, that that the pen is really in the bag, right, you should be able to understand that Abby does not know that. And where does James think? Okay, that Abby does not know that, and James knows that she does not know that, and so they will guess that it's in the drawer. Okay? So it's the ability to distinguish between what you know and what someone else knows, or perhaps what James knows and what Abby knows.
Modern networks still fail at that?
No, so they succeed. They succeed in this. It's not particularly difficult. They've also seen a gazillion examples of that in the training data. But the thing is that this is not a very strong test, right? Because it's really a logical test. And people often, when they think about theory of mind, they don't think only about, have a complete self-contained test and just figure out what the right answer is, right? It's not solving a logical puzzle. So, for instance, just examples, right, that I played around with. Sally absent-mindedly places her car keys in the bathroom. Sally goes to the living room and moves the car keys to the designated place. And I ask, try to, to change the stories in all sorts of ways, doesn't really seem to affect the model in any way, right? Also, when you ask it, what would happen 10 years later, they would, they basically look at it as a pattern or as a logical problem, and not as one where you need to figure out what's relevant and what's not. The way that what we expect to do or hope to do is to use detective stories as a test bed for theory of mind, Because if you buy the notion that really for writing effective fair play stories you need to maintain at least two different perspectives and to balance between them, then perhaps this is an interesting way in which you can actually have a more, I don't know, naturalistic or a more, you know, less self-contained logical setting in which you can see whether you can, you know, entertain these different perspectives simultaneously. Okay, so thanks a lot. Eitan Wagner really did most of the work, of course. He's the person who gets the credit. Renana, my colleague. And thank you for listening. We have a preprint, so go ahead and read. And we still have a couple of more minutes for questions. Yes?
I'm curious, like, how would I interpret that result that the stories that the LLM generate, in those stories, the surprise and coherence are uncorrelated. Like, how should I interpret, like, what exactly are the LLMs? Because the LLMs are trained on the same stories that have high correlation between surprise and...
Okay, that's an interesting question. Okay, I got it. So our argument was basically, so why did we end up doing this experiment and viewing it as validation? Because in a sense, I mean, I think the H null is exactly what you know, what you're saying. This is what we should expect, right? We have better and better models, right? And better and better models. And as the models get better, they are able to follow the instructions, even complex instructions, better, right? And so you would expect their compliance with different constraints to be correlated, right? Because all of these things are correlated with their underlying notion of quality, okay? But the reason that we did not expect this to be as neat as that is because for what we expected was, and we think that there is some clue in our results that this is the case, that it is in fact difficult for language models, despite the fact that they have seen so many whodunit stories, and they all have a fairly typical, you know, structure of this balance between. Despite all of this, it is difficult for them to learn to maintain this balance, okay, without some kind of, I don't know, perhaps additional bias or additional guidance. So they really fail at this, despite the fact that they have seen so many examples. Now, perhaps I should link this to a kind of a broader, I think a broader move in AI, which I particularly, I'm very sympathetic of, which is sometimes called the neurosymbolic approach, essentially saying, okay, so we have these LLMs, right? They do wondrous things, and things we didn't even imagine are possible with this machinery up to a couple of years ago. But they fail systematically because they are unable to represent, to maintain kind of symbolic type level representation. So representations that are, you know, separate from the specific instance in which they work, but rather have some kind, knowledge representation. That's not really what they do. Okay, so in cases where you have a particular schema, you know, a certain convention that you can define and cast symbolically, then in that case, they would, despite the fact that you instruct them to follow it, whether explicitly or implicitly, it would still be difficult for them to comply with it. Okay, so I guess what I believe to be the case is that language models will not be particularly good with the more nuanced conventions, right? That really that you really need to, to maintain this delicate balance between conflicting things, and you really need some kind of outside parts of the machinery to maintain this balance, okay? Some kind of knowledge representation, or some kind of, I don't know, something else. So perhaps I kind of took it a bit.
And so you would expect that humans have that.
Those
writers.
I think so. At least the ones who look. Writing good detective stories is difficult for humans too, right? But at least I expect more successful ones, the ones who are actually able to succeed in this delicate, I would expect them to have that, yes. And I don't expect, but this is of course still an open question, I don't expect just black box training over gazillion examples of detective stories to be sufficient.
So you had this idea of all possible stories and distribution of them. How is it conceptually different from a noisy inference? Let's say there is only one story which is a correct story, but at each step you gather some noisy evidence, not necessarily the good evidence or something,
Okay.
and then you need to infer the story from that. So that's constituting a more known kind of paradigm.
It's better known than you think, because this is just very, the inference here is trivial, right? It's just sample from
Not mathematically. I mean, is different than just having, because then the notion of coherence. You have a real story behind it. The story is coherent. You don't need to introduce something. It's only a question about how noisy the environment is, about the clues.
So
how many clues do you need?
So basically, you're saying that I should model the story generating model as one with a true story plus noise.
It's a noisy observation, and then you have the reader is the inference.
But wouldn't that, I guess, our consideration was that we really wanted to take off-the-shelf models, maybe build an appropriate problem.
Because you can give them a real story.
And then ask them to perturbate it in a sense?
Or even you can construct a full story with all the characters, what all of them have done at every point in time, and then you walk through the board, right, of which information you get.
Right. That's a cool idea. Thanks. Okay, so I guess we're out of time, but I'm still around if you have more questions. Or thanks for the invitation. כן? אתם מסכימים? מאיזה כיוון? כלומר, אפיזודה הוא חוליה בתוך סיפור בעצם? או שהוא כל הסיפור?
לא,
גם לסרטן יש סיפור. אז איזה סוג של סרטן? מדהים. כן, כי אנחנו ניסינו בדוקטורט שלי, ניסיתי לעשות את זה בלי דאטה, את יודעת, בלי באמת דאטה אינטרנטית, דאטה על סמך הספרות, כאילו, בעיקר הספרות הטיפולוגית, כאילו על ידי השוואה בין שפות, לראות איפה הם חותכים, את יודעת, למה הם עושים לקסיקליזציה ולמה לא, מתוך הנחה שדברים שמקבלים לקסיקליזציה אפשר לחשוב עליהם איזשהו לפחות לקסיקליזציה, כבעצם מתארים אירוע, ואז את יכולה להסתכל על תבנית קרוס-לינגוויסטיק, כאילו, ולראות מתי זה נחתך ומתי לא, אבל בסוף הגעתי למסקנה שזה בעצם בלתי, זה insufficient data, כאילו זה לא מספיק כדי לקבוע, אז זה מגניב, אני אשמח לשמוע על זה עוד, כאילו...
סתם כי זה קשור לזה.
Hey, that's very interesting. So, do you look at the internal representations of the network? Can you look at it?
In some of them we can, right? In the open weights one, the proprietary models, sometimes they give you, right, the upper log, right, the higher log probes, but they truncate the distribution at some point. But of course, we can look at them for some models, right?
But I'm curious, like, if you can see the process of a detective story, like
convergence,
like how, yeah, exactly. So how, what actually happens within the network versus, I mean, of course, for a real human writer, you can interview them to understand how. Like how divergent the story generation process would be
Yeah. Did the story generating model decide right before? You mean before say the reader decided?
Exactly.
These kind of questions. Yeah. So we tried to look at that at some point, but I think our interpretability techniques, at least for LLM interpretability techniques, are very limited in the type of insight that they. I don't know if you've worked with this kind of stuff. Yeah. So. I know many people try to take inspiration from neuroscience, right, about how to study these things where you, perhaps in this case, understand the type of dynamic, but you don't really understand how decisions are made.
Right,
in a sense.
When you can also probably look into this concept of world models that you talked about, right, and how the LLMs were lacking the knowledge structure.
Yeah.
If we can try to look into the representations of the knowledge structure inside the LLM's representational capacity, like do they have like cognitive mapping? If they can connect the right dots in the right sequences, that would maintain coherence like a human writer would.
Yes.
So, like that line of investigation, that's what I'm.
So it looks fascinating. I mean, I think that was one of our initial ideas, you know, how to progress. But we just found it, we at least found the inventory of methods that's used today for studying LLMs to just not be particularly convincing for us. But yeah, but I agree with you. I mean, if you're interested, if this is type of stuff that you're interested in, you know, I'd like to continue talking about it.
I mean, I'm very interested in neural data analysis, but that's what we do a lot.
Yeah.
But I could imagine some of that getting transferred, but again, I have no idea about the LLM.
I mean, I can imagine too, right? I mean, it's very likely to be the case, right? That same ideas would transfer, because at the end of the day, we don't use anything particular to the, you know, usually, at least our interpretability techniques, they're not very particular to a specific implementation, right? Or a specific neural architecture. They're kind of generic, but maybe this is not the case with neural data.
Yeah, probably.
Yeah.
I would have to think how the LLM structure would. How would you even start analyzing the representative? Would you consider the different layers separately, or would you pool all of them together?
Yeah.
Which is what we currently do with.
I'd be glad to talk about it. I mean, I'm sure you're more knowledgeable about this.
I mean, it's just in my little part of the brain that I look into. But no, this is actually interesting. Maybe
Maybe we can set up a meeting.
Yeah.
Okay, great. So
Okay.
I'll write you an email.
Okay, awesome. My name is Ronak.
Yeah, we corresponded, I
Yes,
think, around
you asked me.
cognition last year.
Yes.
Around
correct.
the
Yeah.
program.
Yeah. Okay.
Okay.
Thanks.
נורא מעניין מה זה לא נראה אפשר לך
כן, תחום שאני לא כל כך מבין. אני יודע שאתה...
יש שני סטים די דומים לסיפורים האלה. אחד זה מה שנקרא אוסף של הפורלים של בר, שזה 600 יצירות. זה מין תורה של ההרמוניה. יצירות שונות שלו. הרמוניה זה יצירות של 16 תיבות, יצירות יחסית, 4 קולות תמיד, וגם שמה יש את העניין הזה של טרייד-אוף בין הסכמה לבין הלא צפוי.
כן.
זה דבר אחד, והסט השני של היצירות שנמצאת אליהם בתור משהו שיכול להיות מעניין להסתכל עליו בסיסים כאלה, זה היצירות מה שנקרא של שיטת 12 טונים.
אוקיי,
הטכניקה שהתחילה בחצי הראשון של המאה ה-20 בתור ניסיון לכתוב
בצורה הכי אפשרית אגרסיבית, לא בסולם. אז יש כלל לוקאלי. הכלל לוקאלי אומר שאתה לוקח את 12 הטונים של הסדרה של הסולם הכרומטי, מדו לדו, כן? אתה בוחר סדר,
כן.
ואז אתה חייב להשתמש בסדר הזה לכל אורך הדרך. עם קצת וריאנטים, כן? מותר לך להפוך את זה, מותר לך להגיד את זה משהו להתחלה, או דברים כאלה, אבל אתה חייב להשתמש בה. עכשיו, זה מייצר יצירות שהן מאוד מאוד לא נעימות לאוזן.
כן.
אבל שבמסגרת תקופתן הן נחשבות השתמשו בזה בשנות ה-20, 30, 40, אחר כך נמאס לאנשים.
זאת אומרת, ובכפוף לאילוץ הזה, מה הם מנסים? מה, להפתיע?
לכתוב את הדבר הכי יפה, הכי מדבר, הכי... ויש יצירות נפלאות שנכתבו בשיטת המסורתונים. יש יצירות שהן נעות על תחום מאוד גדול מבחינת אקספרסיביות. יש 3 מלחינים בעיקר שכתבו, אורן שיינברג ושניים תלמידיו, אלון ברג ואנטון פון ובר, שכתבו בשיטת 12 הטונים. אז השאלה היא מה באמת, כאילו, מה גורם ליצירה שכתובה לפי סכמה כל כך קיצונית בקביעות שלה להיות יצירה שאתה תגיד עליה שהיא יפה או גדולה.
כן, כן, כן. ויש עבודות חישוביות על ה...
אני לא חושב. על הקורלים של באך יש הרבה, יש אנשים השתמשו כבסיס נתונים לכל מיני דברים שקשורים לעמוק של מערכות הרמוניות. בכלים האלה אני לא חושב שהסתכלו עליהם.
מעניין.
אז זהו.
כן, זה באמת המקרים האלה שבהם אתה בכלל יכול להגיד משהו על... זאת אומרת, אנחנו מראש חיפשנו מקרים שאתה בעצם יכול להגיד משהו על איכות דרך תבנית בעצם. כי הרבה פעמים זה איכות הרבה יותר חמקמקה מזה, נכון, בסיפורים, ואני מניח שגם במוזיקה, וכאילו באמת בעניין הזה של...
יש מקורים שבאך למשל דוגמאות דברים מפורשים שבהם אנשים אומרים, הנה, כאן הוא עשה משהו לא רגיל וזה מה שהופך את זה למאוד מאוד יפה, מאוד מיוחד.
כן.
מופיעים שם אינטרוולים שאסור לשים אותם, אבל הוא יצר אותם באיזשהו... שם צליל אחד בכל אחד, צליל שני בכל אחר, אבל הוא הצליח לייצר אינטרוולים שאסורים כאילו.
כן, אבל בטח משהו אסור אקראי היה מוביל משהו לא מוצלח, נכון? אז גם יודעים איכשהו לתת לזה הסבר? ללמה הבחירה הזאת הייתה...
כמובן, יש שם תפקידים, שוב, יש משהו במקרה הספציפי שאני חושב עליו, יש שם אינטרוול של מה שנקרא טריטון, שהוא מאוד נדיר במוזיקה קלאסית, אבל מאוד דרמטי. הוא מייצר את הטריטון במקום שבו בצורה, כאילו, לפי כללי ההרמוניה היה אסור לשים אותו, זה אכן מייצר את הדרמה הנדרשת.
כן.
ויש לזה סיבות, יש לזה תוצאות וזה, אבל... אגב, אותו קורל, אחד מהמלחינים של 12 הטונים, אלון ברג, לקח אותו והשתמש בו כנושא לווריאציות באחת מהיצירות שלו. זאת אומרת, יש... שני הסטים האלה מדברים אחד עם השני.
מעניין, תודה על ההפניה. נסתכל באמת על... כאלה חפש חשוביות, לפחות לגבי באך.
קורלים של באך.
יש לך לבטח?
כן, נראה לי שכן, רגע, אני לא עם אשתי. כי היא מחכה לי.
סתם כי אולי ראיתם מהשאלות שזה נורא קשור לכמה שאנחנו עושים.
כמה דקות בטוח יש לי.
כיוון אחר לגמרי.
אוקיי, אתה רוצה ללכת לכיוון של מנמוס? בסדר?
יש לך. יש רבע שעה ואני יכול לעשות את זה.
אוקיי.
לא, אני יכול לספור את זה.
רגע, אז אני לא צריך לספור פה כלום, שכן.